Okay, so hopefully we are back live. Probably. I think so.
Hopefully the stream is working. This time I actually accurately wrote what I was doing.
Oh no. Okay, so I'm reading the wrong thing right now. See what happens when that happens. I need to like refresh my screen. Going live is not always the most efficient. Yeah. So Google Chrome is having an issue for me. Uh, awesome. I am back
Oh no,
on.
okay, so I'm looking.
Perfect. Mozilla able to use that just fine. So we're gonna switch. I think we're all the way down to yes. We're going through signal routing. So again, for anyone who's like, "What the heck is this video?" Doing a little Chloe smoothie with Chloe in the morning stream. I have my smoothie here. I am Chloe, co-founder of the marmaj Foundation. I generally try and spend most of my mornings and or days researching ways to leverage Web3 for social good, and currently, I guess, on a pathway of just trying to get more into research and digging into cryptography and trying to make sure that my background understanding and knowledge is as thorough as it can be before kind of moving on to next steps. And so this blog was given to me by, I guess, my current mentor, Thor. I have a couple. I feel like I have a couple of mentors, but Thor is probably the most active mentor currently. And they have suggested I go through the number theory blog post on first principles. So this blog post has a few different blog articles in it. The internet, email, and number theory. So the number 3 one is quite complicated and quite in depth and thorough. So it takes me a lot more time to go through it. And so I started streaming it, and I realized streaming probably wasn't the best medium for it, and I'll probably still stream it later on. But I'm starting with these simpler concepts to stream with, at least just kind of for fun. And then like after I get like tired of streaming, I'm gonna go dig through the number theory one and like programming and other kind of more complex topics in the afternoons or evenings. But yeah, I kind of want to get started again, going through where we were with like signal routing. And yeah, I mean, if people have any questions or comments or whatever, you can leave them in the chat. I do this mainly for myself to kind of keep track of what I've gone through and when and what it looked like and what I knew and keep myself accountable. So yeah, I kind of just say I'll do it so that I do it, and then by streaming it, I prove to my future self that look, I did it. So yeah, if anyone's along for the ride, enjoy. It's just gonna be me reading. If you want to read for yourself, the link's in the description of this video, and you'll probably be faster if you just read for yourself. There's lots of instructions. The writer of this blog post did a wonderful job. So you can honestly just read through everything and you'll probably understand it. It's made for a non-technical audience. So I'm gonna just start from signal routing again and just go from there. So signal routing network addresses. Unlike in a fully connected network where each node can simply pick the right link to reach the desired node, a network with relay nodes requires that a node can address each other. Even if a router relays each signal all of its own links to the other node, which would make it a hub instead of a router, the nodes still need a way to figure out whether they were the intended recipient of a message. This problem can be solved by assigning a unique identifier to each node in the network and by extending each transmitted message with the identifier of the intended recipient. Such an identifier is called a network address. Routers can learn on which link to forward the communication for which node. This works best when the addresses aren't assigned randomly, but rather reflect the structure of the network. So we kind of went over this already in the last video, explaining why it's B2C1, why this would be a link B2 or link 2, sorry, and this would be link 1. We're familiar with hierarchical addresses such as postal code, which are known as zip codes in the U.S., and telephone numbers with their country calling codes. Strictly speaking, the address denotes the network link of a node and not the node itself. This can be seen in the node to the right, which is known as B2 to router B and is C1 to router C. In other words, if a node belongs to several so-called subnetworks, such as B and C in this example, it also has several addresses. Just like your phone could have multiple SIM cards in it, have multiple phone numbers, but doesn't, the phone number doesn't really denote the phone, it just notes the address to reach the phone. Routing tables. The process of selecting a path between two nodes across a network is called routing. Routers are the nodes which perform the routing. They maintain a routing table so they know which link to forward the communication for each node. So each of these nodes that has to route has to keep a routing table. This table tells router A, for example, to forward all communication for node A2 to link on link 2. It doesn't matter on which link router A receives such communications. The router also keeps track of how costly each router is. The cost can either be in terms of network delay or economic cost of the transmission based on what providers charge each other. In this example, router A forwards all communication for nodes starting with C on link 4 because the associated cost is lower. So the computer already knows to forward on the lowest cost network based on economic cost or network delay. It's just the most efficient thing. But generally, it wouldn't look like this. An actual forwarding table, right? The routing table contains all routes, but a forwarding table is what the nodes would actually hold. Probably, based on this information, a router constructs the actual forwarding table, which only contains the optimal route for each destination without cost. This makes the table smaller and lookup during routing faster. So the node holds a full routing table and then creates this little forwarding table so that when it actually wants to look up things, it doesn't have to look up through the entire routing table each time, but can just go to the routing table again for the faster lookup, which is better for lower latency, which means you can just get messages through faster. Routing protocol. So routers and the physical links between them can fail at any time. For example, because a network cable is demolished by nearby construction work. On the other hand, new nodes and connections are added to the communication networks all the time. Therefore, the routing tables of routers need to be updated continuously. Instead of updating them manually, routers communicate changes with each other using a routing protocol. For example, as soon as a router A detects that it's no longer getting a response from router C, it updates its routing table to route all communications to C via B. So it instantly knows, okay, this communication isn't coming through anymore. Like in the communication protocol above, I'm not hearing from Alice anymore. I'm going to hang up on Alice and call, Chloe to make sure I can get through to the appropriate place. And so, I guess like the routing table is updated and the costs have updated as well, obviously. So the signal relaying. A signal can be relayed through a network, either with circuit switching or packet switching. And so we're going to go through both of those. Circuit switching. In a circuit-switched network, a dedicated communications channel is established between the two parties for the duration of the communication session. Okay, so simple enough. You have a dedicated communication channel here in circuit switching. The best known example of circuit switch network is clearly the telephone network. In order to make a call, a switchboard operator needed to connect the wires of the two telephones in order to create a closed circuit. This has the advantage of the delay of the signal remains constant throughout the call and that the communication is guaranteed to arrive in the same order as it was sent. On the other hand, establishing a dedicated circuit for each communication session can be inefficient as others cannot utilize the claimed capacity even when it's temporarily unused, for example, when no one's speaking. So just, you open up a channel with someone else, you're able to use it, even if you sit there with your girlfriend on the phone all night long not saying anything, those resources are still 100% used, regardless of, context or, of the conversation. Then you have packet switching. So in a packet switch network, the data to transfer is split into chunks. So these chunks are called packets that consist of a header and a payload. The header contains information for the delivery of the packet, such as the network address of the sender and the recipient. Each router has a queue for incoming packets and then forwards each packet according to its routing table, or more precisely, its forwarding table. Okay. Apart from these tables, packet switching routers do not keep any state. They just keep a state of where they're supposed to send information when it comes to them. In particular, no channels are opened or closed on the routing level. So all these nodes are open, saying if I get something, send it here. They keep track of what's the most efficient and where I should forward stuff by keeping track of all the nodes that they're connected to. and send information to the best or most efficient places. Since each packet is routed individually, they can take different routes from the sender to the recipient and arrive out of order due to varying delays. Okay, so you're just sending packets as fast or as efficient as you can. Since no router has a complex view of the whole network, it could happen that packets get stuck in an infinite loop. Uh-oh, this packet got lost because certain nodes aren't knowing what's supposed to be happening to them. In order to avoid wasting network resources, the header of the packet also contains a counter, which is decreased by 1 every time it passes a router. If this counter reaches zero before the packet arrives to its destination, then the router discards the packet. So like, hey, this packet just isn't getting where it's supposed to go. I know it was sent to me. I'm sorry. This is the whole, dropping the conversation rather than forwarding it. Such a counter limits the lifespan of a packet by limiting the number of hops it can take, and thus is known as the time to live value. There are also other reasons why a packet can get lost in the network. The queue of a router might simply be full, which means that additional packets can all be sorted and must therefore be dropped. Because packets are similar to cars on the road network, some terms are borrowed from the transportation industry. While the capacity of a packet switch network can be utilized better than the capacity of a circuit switch network, too much traffic on the network leads to congestion. I'm sure we've all experienced that, trying to text our friends at New Year's or whatever. Back in the day. Now I feel like it's pretty much just goes through, which is pretty cool. Source and destination addresses. Because routers keep no records regarding the route that a packet took, they just keep record of where they should send packets regardless of where they came from. The response from the recipient has to include the address of the original sender at least. In other words, the sender has to disclose its own address to the recipient in order to be able to get a response. This is why packets always include 2 addresses. Just like mail, in order to know where someone should send a letter back, you put your address on the packet. One of the source and one of the destination. Internet layer. I always like closing these things. Internet layers. The internet is a global network of computer networks. Its name simply means between networks, so the internet. It is a packet-switched mesh network, only with best effort delivery. This means that the internet provides no guarantee about whether and in what time a packet is delivered. Internet service providers, ISPs, provide access to the internet for businesses and private individuals. They maintain proprietary computer networks for their customers and are themselves interconnected through international backbones. The big achievement of the internet is making individual networks interoperable through the internet protocol. Okay, now we're getting to some fun stuff, right? The internet operates in layers. Each layer provides certain functionalities which can be fulfilled by different protocols. Such a modularization makes it possible to replace the protocol on one layer without affecting the protocols on the other layers. So because the layers above build on the layers below, they are always listed in the following order, but then discussed in the opposite order. So again, the application built on top of the security layer, built on top of the transport layer, built on top of the network layer, built on top of the link layer. And then, it's going into what those things are. So the application layer is talking about actual application logic. And so, if we're out there building, Pixel Dapps games, or, the website I'm looking at now is kind of an application, the blog. You have and this is like an application specific resource, like it could be any endpoint, lots of different endpoints. Example, HTTP, which is the website we're on. So security layer. Okay, you have encryption and authentication. So one or both of the parties. So I can read this, for example, but I can't write on this blog and log in and change everything. So the application is built on that security. And I mean, yeah, it's going into like identifiers and like TLS security. Okay, transport layer. Jeez. Typically, reliable data transfer, operating system processes, port numbers, so the ability to actually receive the data that's on this site, and be able to connect to it and all that fun stuff and get the packets. The network layer, so packet routing across the internet. So internet connected machines, IP addresses. So just, so I guess servers talking to each other and making sure that they're keeping everything all set up. And then the link layer that has handling with a physical medium. So actually like plugging my computer into the power outlet and it having its own address and like being able to even, send information out into the great sphere. So I guess Wi-Fi. Cool. We will discuss each layer separately in the following subsections. That's cool. See, I always like just giving my own random thoughts, and then obviously the article will clear up any misconceptions, which is good for myself as well. For now, you can treat the above table as an overview and summary. Before we dive into the lowest layer, we first need to understand what building on the layer below means. Digital data can be copied perfectly from one memory location to another. The implementation of a specific protocol receives a chunk of data, known as the payload, from the layer above and wraps it with the information required to fulfill its purpose in the so-called header. The payload and the header then become the payload for the layer below, where another protocol specifies a new header to be added. Excuse me. Each of these wrappings is undone by the respective protocol on the recipient side. This can be visualized as follows. So, the sender interacts with an application, there's a security layer wrapping it, a transport layer wrapping it, a network layer wrapping it, a link layer, their actual computer wrapping it. Then it gets sent. Okay, then when the receiver receives it, it goes through the link layer, network layer, up to the transport layer, security layer. But it's just the recipient's protocol, I guess, understanding how to unwrap each of these layers and get back to the application layer information, which is like me reading this blog and someone else writing this blog, I guess. It's pretty cool how much has to happen for that to actually, go through and me to just read something, which is pretty awesome. While this graphic is useful to wrap your head around these concepts, it can be misleading in two ways. Firstly, the payload can be transformed by a specific protocol as long as the original payload can be reconstructed by the recipient. So like these colors in the middle can be switched to all different types of things. Examples for this are encryption, obviously, and then redundant encoding for automatic error detection and correction, yes. Like erasure coding and all that. Secondly, a protocol can split a payload into smaller chunks and transfer them separately. It can even ask the sender to retransmit a certain chunk. As long as all the chunks are recombined on the recipient side, the protocol above can be ignorant about such a process. As we've seen in sections above, a lot of things can go wrong in computer networks. In the following subsections, we'll have a closer look on how protocols compensate for deficiencies of the underlying network. Before we do so, we should talk about standardization first. So, request for comments, RFC. When several parties communicate with each other, it's important that they agree on a common standard. Standards need to be proposed, discussed, published, and updated to changing circumstances. I'm not aware of any laws that impose specific networking standards outside of governmental agencies. The internet is an open architecture, and technology-wise, you're free to do pretty much what you want, anything you want. This doesn't mean, though, that others will play along. If different companies shall adopt the same standards to improve interoperability, it's very useful to have independent working groups in which proposed standards are discussed and approved. For internet-related standards, such an open platform is provided by the Internet Engineering Task Force, IETF. With organizational and financial support from the Internet Society, workshop participants and managers are typically employed by large tech companies who want to shape future standards. The IETF, the Engineering Task Force, publishes its official documents as Request for Comments, RFCs. This name was really chosen to avoid a commanding appearance and to encourage discussions. In the meantime, early visions of potential RFCs are published as internet drafts, and RFCs are only approved after several rounds of peer review. RFCs are numbered sequentially, and once published, they are no longer modified. If a document needs to be revised, a new RFC with a new number is published. An RFC can supersede earlier RFCs, which are then obsoleted by the new RFC. Sometimes RFCs are written after the documented technique has already gained popularity. Even though the most important internet protocols are specified in RFCs, their conception and style is much more pragmatic than similar documents of other standards organizations. The first RFC was published in 1969. Since then, almost 9,000 RFCs have been published. Oh my gosh, that's amazing. I did not know that. Not all RFCs define new standards. Some are just informational. Some describe the experimental proposal, and others simply document the best current practice. That's awesome, though, having that many standards. I think NEAR needs to do better at the way, I guess, we handle standards, if I'm a NEARian. But we're actually working on a more for fun standard at NEAR, kind of just like a for fun like application support burn standard. But yeah, very cool. They call them NEPs at NEAR. So the link layer, protocols on the link layer. Oh my gosh, sorry. Take care of delivering a packet over a direct link between two nodes. Examples of such protocols are Ethernet, and Wi-Fi. Link layer protocols are designed to handle the intricacies of the underlying physical medium and signal. So actually plugging your computer into it, or having like a Wi-Fi device in your computer. This can be electrical signal over the copper wire, light over the optical fiber, or an electromagnetic wave through space. The node on the other end of the link, typically a router, removes the header of the link layer, determines on the network layer on which link to forward the packet, and then wraps the packet according to the protocol spoken on that link. So all the information is there. Link layer protocols typically detect bit errors caused by noise, interference, distortion, and faulty synchronization. If several devices want to send a packet over the same medium at the same time, the signals collide, and packets must be retransmitted after a randomly chosen backoff period. So there's a lot of stuff in here. We're going to go through all of it for the link layer. And I think, honestly, I'm probably going to leave this video here and just go through all the layers in one video, probably tomorrow, I guess. And then I'll start going through the email article, which seems really fun. Shouldn't take too long. There's quite a bit of information here, but it seems like it'll be a good one. But by Thursday, Friday, should get through this one. And then we'll go back. I'll start going back through number theory, hopefully by the end of the week, maybe Monday. I'm still going through it on my own, of course, as I said previously, the number theory article. But for actually streaming it, I feel like I should read it on my own first, maybe parts of it a couple times, and go through more of the math before I just come on here and start talking about it. It gets a bit deep past where I was going. So yeah, I'm probably going to do a stream a little later on, digging into more Pixel Pet stuff, I think. For the marmaj Gaming DAO, we have a new page out. I want to kind of go over that page as well. So I'm probably going to go to the bathroom, finish my smoothie, and I'll probably be here streaming again after I go walk Mika or something. But hope everyone's having a great day.